Okay, guys, welcome to this final video concerning this review for exam 3. I know that the links for the previous ones have been posted on Canvas, so hopefully you guys will have a chance to go through them. If not, you can always come to YouTube and here and find them. Anyway, basically so far we're missing problem 9. Okay, we didn't do. And then let me pull that thing there that I was working off of. So problem 9 we didn't do, and I promised to come back to it. We did all of the other questions, okay? And then also I believe we didn't do problem. We did this problem, so the last problem also we didn't do, namely. So I'm going to do the last problem first, and then I'm going to come back to problem 9. So it doesn't mean that anything is more important in terms of concepts than the others. They're all important in terms of concepts. This exam covers three chapters, 9 about collisions. Chapter 10 and 11 really deal both with the rigid body, whether in the case of the first one, the dynamics, pure dynamics, or the second one, which is the angular momentum. So let's finish this problem. And this problem is actually one of the problems that deal with the angular momentum. So let's do that. And that's problem 12. Problem 12 says that you have a cylindrical turntable of radius 1.9 meters. So the radius of this turntable is 1.9 meters. This is R supposedly, okay, and of mass 30 kilograms. So the mass of the turntable is M, which is 30 kilograms. And let me move down a little so that you can get a little bit of working area. We can do it that way. So let's see it. No, oops, I didn't mean to do that too. Okay, I guess if I do that, I can get more real estate that way. Okay, good. So the point being in here, this is some of the information that's been given to us, and it's spinning counterclockwise in a horizontal plane with an initial angular speed, omega. So I'm going to write it omega naught is 4 pi radians per second. Okay, that's the speed of rotation, how much it's going spinning. The fixed turntable bearing is frictionless, so we're going to neglect friction. A lump of clay of mass M equals to 2.25 kilograms. That's a big amount of clay. And negligible size is dropped, so it's a massless basically. So we're going to deal with it as a point particle. So we're not going to worry about its internal moment of inertia. And it's dropped onto the table from a small distance, meaning, so this is the turntable. So you come in here and you drop some clay, okay? And it's spinning counterclockwise. This is omega naught just above it so that you don't have any kick to it, okay? You don't give it an additional or subtract from it. So if you come at an angle or something, you might give it a change its angular moment. It may have already an angular moment. This way, it's omega, initial omega for this particular clay is 0, okay? So this is the initial for that because you drop it immediately above it very gently, okay? And of course, and it sticks to the turntable at a point of distance of R equals to 1.8 meters. So this is R is 1.8 meters, okay? And find the final angular speed of the clay. Okay, we're going to use conservation of angular momentum. So we're going to say I initial, I1 times, or I naught times omega naught. This is before must be equal to the final, which is, I'm going to call it IF omega F. That's the question we want to find, omega F. So this is the angular momentum. Remember, it's by definition, it's not by definition. Yeah, it's actually, we arrived to this value from the lecture that it's I omega, where omega is the angular velocity and I is the moment of inertia around the axis of rotation. In this case, it's the center. It's spinning around that. So initially, since it's a cylindrical shape, okay, the angular momentum is 1/2 of mr squared. At the end, the angular momentum is going to be that, which is I naught, plus the mass times r squared, because this is treated as a point particle at distance r from the center of rotation. Okay, so that's the final momentum. And therefore, the omega f from this expression, basically, is going to be I naught over IF times omega naught, And so basically what I have is I have 1/2 of mr squared divided by 1/2 of mr squared plus mr squared, lowercase, times omega naught in this case, okay? Because that's the I naught times omega naught. So if we do the math in here, technically, usually what we do in this case, we try to make it as dimensionless as possible. So what we can do in here is omega f equals to 1 over 1 plus, when I divide by 1/2 of mr omega naught squared, so I have an omega naught in here. This will leave me with 1, this will leave me with 1, and here I'm going to have 2 times m over big M times little r over big R squared, okay? So that gives me a value for omega final. Basically, I have omega naught, which is 4 pi. I have the M mass, which is 2.25 times 2. That's about 4.5 kilograms divided by 30. And the radius is 1.8 over 1.9 squared. So it's going to give me a value in here for this whole expression, and should be less than 1, meaning this one less than 1. So omega f should be less than 4 pi radians per second. Of course, it was spinning, and now you add something to it. Its moment of inertia increases, therefore it's going to slow down. That's basically what this is, and you can find exactly how much. Is a mechanical energy of the turntable constant? And this explain without this is an inelastic collision. Actually, it's a perfectly inelastic collision because of the fact that they stick together and they move. Therefore, the mechanical energy is not conserved because there is no potential energy. The whole thing is just staying on the same level, so there is no increase in height, or because we dropped it from very little distance, so there is no change in the potential energy. The change in the kinetic energy is the change in the total mechanical energy. This is an inelastic collision, therefore the mechanical energy, the kinetic energy changes, which means that the mechanical energy is not conserved. Okay, is the momentum of the system constant in this system, in this process? Of course, it's constant because it's all internal processes. There is no external torque that causes it. Okay, so that answers this problem. Let's move on to the, oops, why did I do that? I was really trying to get more real estate. So I guess I can do the mouse again and be a trick. Anyway, so let's go to problem 9 because I deferred it now long enough. So we really have to come back to it because it requires a little bit of work in here. And this is actually from chapter 10. So you have an incline in here, and you have mass 1, you have mass 2 on the incline in here. The angle theta is here, and there is a pulley, and this pulley is not massless. Actually, it has a mass where the rope goes around it. Okay, so we were asked to find the free body diagram. That's question number 1. Draw the force diagrams for of the two blocks and the pulley. And the problem, M1, which is this mass, and M2, which is this mass, and big M and big R, they are all given, including the coefficient of friction. M1 is equal to 2 kilograms, M2 is equal to 6 kilograms, and big M is equal to 10 kilograms. That's the pulley. And the radius of the pulley R is a quarter of a meter, 25 centimeters. And the string is massless, so we're not going to worry about it. And the fixed wedge-shaped ramp has theta equals to 30 degrees. We need that. And also coefficient of friction, kinetic friction is equal to 0.36. We have all of this information. And what else do we need? That's all we need right now. The other thing is, okay, so we're good. So we need to draw the free body diagram. Oops, what is this popping up in here? Anyway, so M1 has M1G has the normal. I'm treating it as a point particle. Has the tension on this side of the pulley, which I'm going to call it T1. So this is side 1, this is side 2. And since most likely it's going to be moving in this direction, so the force of friction on it is going to be on this side. And I'm going to put it F of friction 1. Actually, usually use the lowercase f. Okay, F1. Okay. And it's going to be kinetic friction, so we're not going to worry too much because it's going to tell me if it's going to be moving. Of course, if we find acceleration that is 0, that means we have to redo the calculation because it's not going to work with the kinetic friction. since we're not given the static friction, therefore most likely that's the only way. So we're not going to find an acceleration that is 0. In other words, I'm assuming this whole thing is moving in this direction because of the fact that you have M2, which is bigger mass, 6 kilograms, versus M1, which is 2 kilograms. So most likely that's a good scenario, and the direction of friction is good. So the acceleration should turn out to be a positive number. Anyway, that's M1. So the forces are T1 and F of friction pointing in the opposite direction, and the two forces in the vertical direction. For the pulley, okay, it has basically in the where the support is, and I drew it a little bit kind of tilted, but it's supposed to have M1 or a big MG pointing down, the normal versus the support on it. So I'm going to leave this one as N1, and this one is N. On both sides of the pulley, there is a tension T1 and there is a tension T2. I know T1 is not this T1. The magnitude, they're equal in direction, they're opposite. Okay, so those are the only forces on it. Okay, finally, the last one is this incline shape. So I have M1G or M2G, I'm sorry. I have the normal, which is making an angle, which is N2. And I have the tension, which is the same tension in magnitude as this T2. So I'm going to give it the same symbol. Granted, the direction is opposite to this T2, okay, because the string is massless. And we have a force of friction also on it. So I'm going to call this one F2. Okay, so that's it. And the assumption is that it's moving down. So this is the answer to question 1. Determine the acceleration of the two blocks. For that, we have to use basically Newton's laws of motion combined with the torque equations and all of that. Okay, for this one, I have the equation that basically says M1G plus the tension T1 plus F1 plus N1 equals to M1A. Okay, and it's the same A all the way throughout because the string is supposed to be stretching, so basically doesn't stress. That's an assumption I have to make in here. So this acceleration A is the same acceleration with which this one is. Furthermore, because the pulley is going to be turning on its circle, around, and we're going to assume that it doesn't slip, the rope doesn't slip on it. So the displacement along the arc displacement, which is the same displacement of the two masses, so is equal to the radius r times the angular displacement theta in this case. In other words, when I take the derivative of this quantity twice, I'm going to find the acceleration on one side, r is constant, I'm going to find alpha on the other side. So the angular acceleration for this pulley is related to the linear acceleration of both masses through this relationship. Okay, that's a condition of no slipping. Furthermore, what do we need? We also know that in magnitude, F1 must be equal to mu k N1, okay, because it's kinetic friction. And the other relationship that we know also is that M2G plus the force of the tension T2, in this case, plus the force of friction, which is F2, plus the normal force, which is N2, must be equal to M2 times the same acceleration A. Okay, and also in magnitude, the force of friction, F2, is mu k N2. Okay, so we did this problem several times now, at least some similar to this problem. So for the incline, I'm going to have the direction of the incline as the x-axis, and the direction perpendicular to it is the y-axis. So in the perpendicular direction, so I'm going to put the inward down as negative. So it's going to give me minus m2g cosine of theta, that's this term, plus the tension is going to have 0 components along the vertical, along the perpendicular to the incline. So it's going to be 0 plus 0 for the force of friction, and N2 is exactly in that position, and there is no acceleration. The mass is not going up and down. So I find the relationship between N2 and the weight of this mass. So now we have N2, which we're going to plug in here, and we're going to find the force of friction. Okay, same thing. On this one, the horizontal displacement is where the acceleration is for mass M1, And the vertical displacement is where there is no motion. So the mass M2 is not going up and down. So again, I'm going to take the downward, the upward direction is positive. So M1G is negative M1G. The tension has no components along this direction. The other tension also has the other friction has no component also in the direction. And N1 is positive, and there is an acceleration in this direction. So N1 is equal to M1G. Okay, which means that I can already find this force of friction, F1 in magnitude. Okay, the other two directions should give me the relationships I need. So in the incline, in this equation, on the incline, what I'm going to find is, first of all, M1G will have a positive M2G will have a positive M2G sine theta. That's the component along the incline of the mass of the weight. The tension is negative T2. The friction is negative F2, and there is no normal component in this direction. And of course, it's M2A, okay, in magnitude. That's one equation. I already have the force of friction, so I really should have subbed for its value. This term in here, I am going to write it as mu k times M2G cosine of theta. That's the only thing that is. So in this case, I have an equation that basically reads mu k, M2, and G in cosine theta, they are all known. M2 G sine theta, they are all known. And what we don't know is this tension, but we don't know the acceleration. So this equation isn't going to help us because we don't have two unknowns in it. Okay, let's go to the other equation now. And that gives me, I'm going to label it as equation 2. So that gives me in the horizontal direction, the weight has no component. The tension is positive T1. By the way, you can see it's positive in the positive direction, minus the force of friction F2 and F2, I'm sorry, F1. I'm looking at equation 2, so it's F1. F1 is mu k times M1G, and there is no component for the normal is equal to uh, M1A. Okay, the good news is, so there is some good news and some bad news. The good news is now we have another equation. Remember, we had one equation with two unknowns. We have another equation, but we introduced another unknown, namely T1. So we don't know the tension T1, we don't know the tension T2, and we don't know this acceleration. So we have two equations with two unknowns, two equations with three unknowns. That's not good enough. We need another equation, and the other equation comes from the torque equation for this pulley. So what I'm going to do in here, I'm going to take the center of rotation as being the where it's rotating from. So in this case, the normal and the M1G or big MG will have no torque. So the only torques that are going to be is T2, which is a torque in the same direction as the angular acceleration. So I'm going to take this as a positive direction so that I have on the other side a positive number. So this is what I meant by the equation, okay? Normally, the equation reads as sum of the taus, sum of the torques, which is equal to I alpha. So in order to project this one in the in direction where this side is positive, so I'm going to take the direction of alpha. Alpha is clockwise. So I'm going to take that as a positive direction, which means that T2 has a positive torque, whereas T1 has a negative torque. That's the only thing. And both of them are tangential, so their torques are going to be the force times the radius. That's all. Okay, so T2 times R minus T1 times R, already projected in direction of motion, which is in this case clockwise. So it's going to be equal to I alpha. Okay, so we have a new equation now. Third equation, which I'm going to label it as equation 3. And it has apparently the two old unknowns, but there to introduce a new unknown. But that unknown we know is a relationship to one of the unknowns. Alpha is just A over R. So this alpha is simply equal to A over R. So this equation is I times A over R. So having said that, and this is T2 times R minus T1 times R. So basically, this is the equation 3 really, how it should be read without that additional unknown alpha. So now you have three equations with three unknowns, so you're in business. Okay, what is I, the moment of inertia? This is a cylindrical shape because we're going to assume that it's some sort of a disk, and it is, okay? And so the I in this case is equal to 1/2 of mr squared. And having said that, equation 3 now is going to transform as the following. I'm going to divide all the way throughout. So I'm going to have by r, I'm going to have an r squared in the denominator. So it's going to be t2 minus t1 equals to I, which is in this case 1/2 of mr squared times a over r squared. Remember, there is an r in here that I took downstairs in here, and I have an r squared. That is exactly the quantity I need to cancel this r squared. And this is basically the equation. Let me rearrange them all so that you can see them. So equation 1 basically was saying that m2g sine theta minus, I'm moving this mu k to the other side in there, mu k times m2g cosine theta, and I have minus t2 is equal to m2a. That's one equation. This is equation 1, okay? Equation 2, I have T1 actually in it. T1, I wrote T1 minus mu k, M1G is equal to M1A. So this is equation 2. And the last equation in here, equation 3, it says T2 minus T1 is equal to, of course, I have to do these cancellations in here, and it's equal to MA over 2, okay? So typically, when you're facing this problem, you add all sides of the equation, and you can clearly see that the T2 here and the T2 here, they cancel because one of them is negative and the other one is positive, and the T1 and the T1 cancel. So at the end of the day, you'll have a bunch of constants in here. And on the other side, it's simple. On the other side, when you add the equations, it's going to be M1 plus M2 plus big M over 2 times A. Okay? And on the other side, you have all the knowns of the problem. So you have M2J. So I'm going to take G as a common factor, and that's it. So I'm going to take G as a common factor because of an acceleration, and the terms inside are going to be the masses, basically. I have M2 sine theta on one side. I have minus mu k, open parentheses. I have M2 times cosine theta, and I have M1 on this side. And that's basically the entire expression. From here, you can solve for A by dividing by this sum of masses. One of them is half of it. So you have found the acceleration of the two blocks. If you're curious trying to find the angular acceleration, all you have to do is just divide this by the radius of the thing. And then it's asking you for the tensions. Okay, once you find the acceleration, you can come to either equation 1 to find the tension T2, because then you have the acceleration on this side and everything else is known, so you find the tension T2. Once you find the tension T2, the easiest way to go is go to equation 3 actually to find the tension T1, because T2 is known, minus in this case, you move this one, m times A over 2, since you just computed A, so you should be able to find T1. Or if you wish to go to equation 2, in this case, and find T1, because it's in terms of mu k m1g plus m1 times the acceleration that you just computed. As a matter of fact, these two equations serve as a mathematical check on your answer. I hope that this has been helpful. This is the entire review. So please, if you have any questions, please do ask them. I'm going to post this stuff in here on YouTube, and I'm going to post them on Canvas, and we're going to have more discussions in the classroom. Thank you.